So in our last module, we discussed security policies on our vSwitch and our port groups. In this module, I want to discuss uh, vSwitch and port group traffic shaping and our teaming and failover policies. So let's start off with traffic shaping. Let me just get my vSphere web client up here. Alright, so we'll continue working with ESXi1, which we have been using. So I'm in my host and cluster view under ESXi1, manage and networking. Okay, so then I'll go to edit my settings for this vSwitch, which is vSwitch 0. Okay, I click on the pencil icon, the edit settings box would pop up here. We would have covered security settings in our last module. So we'll deal with traffic shaping for now before moving on to teaming and failover. As we can see, by default, the traffic shaping is disabled. Okay, so if we were to enable traffic shaping on this vSwitch, it would be done only for the outbound direction. Okay. Okay, so this is our standard vSwitch. Once enabled, it would be done for the outbound direction. If we were to enable this on a distributed vSwitch, it would be for both the outbound and inbound direction. So we have a couple settings, a few settings we could configure here. Firstly, we have the average bandwidth, and this is in kilobits per second. Next, we have peak bandwidth. This is in kilobits per second too. And then we have our burst size, which is in kilobytes. Similarly to our security settings, the traffic shaping settings could be configured at both the vSwitch level and at the port group level. So we are at vSwitch 0 here. If we were to exit this and then come into one of our port group that is on vSwitch 0, let's just select our testing port group. If you were to go into the edit settings for this traffic shaping here, we have those same settings here with the port group level settings overriding the vSwitch settings once configured. So the average bandwidth here, this is the data transferred per second. All right. The peak bandwidth would be the maximum traffic that the vSwitch could pass before it starts to drop packets or start to drop traffic here. And then the burst size, this is the maximum data in the burst, and this really is equivalent to our bandwidth multiplied by time. All right. So this would be all for traffic shaping. Next, we'll look at our teaming and failover policies. So with teaming, we have multiple uplinks connected to a vSwitch. They would form a team. Basically, you would do this to load share or provide some redundancy for the traffic between our physical and virtual network. This is done to provide passive failover in the event of some hardware failure. Okay. Let's just keep in mind that we could connect only a physical NIC or a VM NIC to one vSwitch at any time. And this would need to connect to the same physical switch or the switch stack at the other end, at the physical end. Ideally, we would configure these interfaces as trunk links and configure the allowed VLAN that we need on our vSwitches. So generally, we should Yeah, so generally we should use care when theming our links. We should try to use adapters from a separate bus architecture. So, for example, if you're building a four adapter Ether channel or a 4-link Ether channel, and we have 4 onboard NICs and 4 PCI NIC, we would try to eliminate a single point of failure by using 2 of the onboard links and 2 of the PCI links to bundle in our Ether channel. Okay. Actually, let me just draw this to make it a bit clearer. So say this was our ESXi host. Okay. This is our host here. In this host we have let's just say we're working with vSwitch 0. We're working with vSwitch 0, and we have let's just say we have 4 onboard adapters here. Let's just call this onboard. And here we have 4 PCI NICs. Okay. And we want to bundle or attach 4 of these adapters to our vSwitch. So say we'll be utilizing these 4 here, 2 from our onboard and 2 from our PCI adapter. And at the other end we have our switch stack. So let's just call this member 1 and we call this member 2. Okay, so these are stacked together. For building of our Ether channel, we would want to take one of these adapters here, go across there, then take another one, come across here, and then we'll do the same on our PCI NICs. Okay, one across there and one across here, and then we'll just bundle all of these here now in cross stack Ether channel. So at any one point, if this adapter was to fail, for example, this PCI card, we would still have connectivity of our vSwitch into our physical network, utilizing these 2 interfaces here. Okay. Okay, so let's now take some time and discuss the different options we have for our load balancing. So the load balancing method used in vSphere, it's a bit different from the load balancing method that is used on routing protocols. vSphere, it is based on the number of connections and not per packet. Alright, so we have 4 different methods of configuring our load balancing on our vSwitch here, our port group. We'll start off with our route based on IP hash. Okay. So route based on IP hash, this uses the source and destination IP address to calculate a hash. Okay. It uses source and destination IP to calculate a hash to determine which physical NIC to use. All right. So once this is calculated, a VM connected to this vSwitch, it could forward traffic over the different physical adapters or VM NIC here. This is the only method that would allow us to form a link aggregation or an Ether channel with our physical switch. Alright, none of these other methods, if we choose this, would allow us to create an Ether channel. So the physical adapters connected to this vSwitch, right, at the other end, should point to the same physical switch or switch stack. So if we had multiple adapters here, we're building an Ether channel connecting this over to our physical network. These should all point back to the same physical switch or the same switch stack. All right. So building Ether channel with our standard vSwitch, like we're seeing here. This would only support the static configuration of our Ether channel. So say for example, if you're building a Cisco Ether channel or aggregating ports on a Cisco switch, we would need to manually create the bundle. We could use the channel group, let's say 1 for example, channel group 1 mode on. We'll need to use that command. And all the adapters that we need to bundle in that Ether channel, we'll need to list them or bring them under active adapters here. So we can have like a 4-port Ether channel with 2 adapters in under active and 2 under standby, for example. We'll need to have all 4 under active. Okay. So basically, we will choose route base and IP hash, and then bring in all our adapters on the active, and that should allow us to create a Ether channel back to our physical switch or switch stack. Next in our list, we have route base on source MAC address or source MAC hash. Sorry. So route based on source MAC hash. This method is almost identical to route based on the originating virtual port, which is the default setting. We'll discuss that next. It's almost identical to our virtual port here, or originating virtual port, except that rather than try to match one virtual port to one uplink, we are now matching different MAC addresses from a VM to their own uplinks. Okay, so the assumption here is each VM have multiple VNICs. Okay, and we are matching those different VNIC MAC addresses to their own physical adapter exiting this vSwitch. So next we have our route based on the originating virtual port. As I mentioned, this is the default load balancing method on our vSwitch. So this method would try to associate each virtual port on our vSwitch to an uplink. And if that uplink was to fail, then it would move over traffic from that virtual port on the vSwitch to another uplink. All right. This would basically guarantee traffic from a particular port. It would guarantee that those traffic are moving consistently over the same uplink. Okay. So in most cases, you would have more VM ports than uplink. So what would happen is you would have more than one VM utilizing the same uplink. Okay. So you could have like 10 virtual machines running on this host with only 1 or 2 uplink. Okay. Finally here for load balancing, we have our explicit failover order. So here it just uses a list of failover adapters starting from the top that are listed here. All right. So coming down in our list here, we have network failure detection. So this could either be link status only or beacon probing. So with link status only, the link status on the physical adapter, that is what determines if an uplink has failed on the physical switch end. All right. So the downside of using the link status only is the ability of our physical adapters in our host to determine a failure of links upstream to our physical switch. Okay. Next in our list here we have beacon probing. Okay. Beacon probing, this uses a broadcast or broadcast traffic to allow excuse me, to allow vSphere to sense when there is a improper configuration. So improper configuration in this case, meaning a VLAN mismatch or some improper spanning tree protocol settings, or if there is a switch failure that is upstream to the physical switch that our host is connected to. So once beacons are not returned, it would move traffic over to an available adapter that is based on the failover order that we have under standby. Okay, so once we're using this, we would have multiple adapters are active, and then we have some listed under standby here. So next we have our notify switch settings here. We have two options, yes and no. By default, this is configured to yes. So the notify switch setting, this would use a reverse ARP to send fake frames on behalf of our virtual machines. Right? So this is done to determine exactly where the MAC address is located. Okay, so let's just recall. The main job of our physical switch is to learn MAC addresses. And if those MAC addresses were to change, to update its MAC address table. Okay? When this is set to yes, we are basically notifying our physical switch of changes in our virtual infrastructure. If the notify switch setting is set to no, okay? If this is set to no, our physical switch at the other end, it would not be notified and would not update its MAC address table. Alright? There are cases when you would want to set this to no, to change it from the default. So an ideal use case for setting this to no is when we're running Microsoft Network Load Balancing in unicast mode. Setting this to yes whilst using Microsoft Network Load Balancing in unicast mode, it would cause problems with the NLB operation. Right? So other than if you're running Network Load Balancing in unicast mode, you'll just want to leave this to the default of yes. Alright? So next, let's take a look at our failback settings. So our failback settings here, we have two options too, yes and no. The default is yes. So failback, the option here determines how our host would respond when a fail adapter is recovered. Okay? So by default, the fail adapter that is now online will take its place back from a standby adapter. So how this works is our VM NICs that are listed here under active adapters. So we the NICs that are listed under active here, these would always be used unless it fail. Okay? If this was to fail, our NIC in here, then our first standby adapter, if we had adapters listed under standby here, our first standby NIC would be used. Alright? So this setting basically deals with if the failed VM NIC comes back online, if it should switch back to that VM NIC or stay with the replacement VM NIC that was under standby. So leaving this failback option to yes, the default, it can cause link flapping or a situation where our system continually try to change between adapters. Changing this setting to no. Changing this to no means when a previously failed adapter, when that failed adapter comes back online, the adapter that took its place when it failed, it would continue to be used. So we may leave, we may want to leave the standby adapter to continue to run or fail back to the original active adapter. Alright? If we were to leave this to the standby, we might end up in a situation where we're utilizing a slower or a less desirable adapter rather than switching back to a higher performing adapter that was running under active previously.